Must bring tutoring to the top.
Now we're going to think about measuring the density of something like this, which is definitely irregular. So you'd see the problem if I tried to measure the dimensions of this rock. It'd be very difficult to decide on any kind of height, depth or width. So we need a different method, so the ruler's not going to help us today. So first thing we'll do that we can measure is we can measure the mass of this rock, so we will need the mass. Now I have got it on a piece of cotton, which you'll see why afterwards. So we're assuming that the mass of this cotton is far less than the mass of the rock, so don't worry too much about the extra mass. I'm going to place that on the top pan balance, and we have 96.3 grams. 96.3 grams. So going back to our formula, we've got density is mass divided by volume. We've got the mass, no problems. We've got a problem with the volume because we said we can't measure it, so we need a slightly different method. Now to do that, we use something called a displacement can. A displacement can we fill up with water, and we fill it up with water to the point where the water just about comes out of this little pipe on the side. So if we go a little bit further and wait till we see a drip. So now we know that the water is at a level where it's just about to come out of this pipe. So anything that we put in that water is going to cause the water to come out of the pipe. This is known as a displacement can because we're going to displace the water. You might have seen it called or heard it called a eureka can. And there's a famous story behind that which your teacher might have mentioned. So once that stopped dripping, about there, okay, we can now catch the water that's displaced. So I'm going to get the rock, and we should just about fit this in. So I'm going to do this, and as I lower it in there, it's going to displace the water, and I'm going to catch the water that's displaced. And again, don't worry about the volume of the cotton. In comparison to the volume of the stone, it's minuscule, so we can ignore it. So once that's stopped dripping, I've now got an amount of water in here which is equivalent to the volume of that rock. So I've got some measuring cylinders, and this is where, if you've got a choice of measuring cylinders, if we'll use the big measuring cylinder first. So if I pour the water in, okay, and we'll take a reading off there. This is about, I can see it's 35 centimetres cubed. Let me just check and then you can have a look. Yeah, it's about 35 centimetres cubed. Now, I could have used that one. This would be a more accurate reading because I've got better divisions between my numbers. But of course, you might be able to see this finishes at 25. So if I put that water in there, all that's going to happen is it's come over the top. So that would be no good. And this would be even worse, wouldn't it? Because that's got a maximum scale of 10 centimetres cubed. So I can't use those today. But if I use this one, I'll take a reading. It's actually a little bit more. To avoid any errors I should really look at, I'm going to say that's 36. So we've got 36 centimetres cubed. So if you look now, we've got our density is 96.3, our volume is 36 centimetres cubed. So I can use the calculator and I can say 96.3 divided by 36 equals, and I have a density of 2.7. 2.7 grams per centimetres cubed. You can check those, I hope I'm right. So very different from the previous method in terms of how we measured it, but in terms of the calculation, it's exactly the same.